Roger, do you want to go ahead and try to unmute?
Yes, can you hear me okay?
Bingo, we hear you great. So I'm going to go ahead and read your bio really quick. Roger is the Associate Division Chief of the Space Transportation Systems Division within NASA at JSC. He is responsible for overseeing the probabilistic risk assessments of all Artemis missions in the lunar surface and the Lunar Gateway space station. His experiences include mission analyses supporting the Space Shuttle, Mars, Constellation, Orion, Commercial Crew, Deep Space Gateway, and the new Lunar Lander and surface programs. He currently serves as NASA's CROSS program PRA lead, responsible for integrating the various human exploration program PRAs, as well as overseeing the development of several new PRA methods for future use and serving as NASA's System Safety Steering Group, Human Factors Technical Discipline Team, and the Integrated Medical Model Steering Committee. Roger's experience is quite broad. He holds degrees from in nuclear and mechanical engineering and a master's in nuclear engineering from the University of Missouri. And we have a longer bio on him in the program that got sent out. So without further ado, we'll get this started. Roger, do you want to just kind of introduce yourself and start, kind of going over the work that the Safety and Mission Assurance team has been doing?
Well, I think the audience has already heard enough about me. Let's go ahead and talk about what I'm here to talk about. I don't have charts, so I apologize for that, but I am going to try to help with a glossary of information, definitions, that kind of thing, for a lot of terms that have been used in the previous speakers that I think would help get everybody on the same page. For example, Artemis missions. That's now the follow-on to the Apollo missions, going back to the lunar surface. The agency lock threshold. Well, first, loss of crew. And really that means probability of loss of crew. And that's the death or permanent debilitating injury to one or more flight crew members. So you lose one crew member, that's loss of crew. When we talk loss of mission, that's the loss of or the inability to complete a significant primary mission objective. And that also includes loss of crew, which is a primary objective, bringing the crew back home safely. We have this Moon to Mars program. It's the new overarching program that we have for the Artemis missions, and as well as leading into the future Mars missions and so forth. So a lot of cool things, but a lot of things that are somewhat unknown to us at this time, as well as maybe underappreciated. We only have 6 data points of missions landing on the moon back in the 60s and 70s. So we had a 7th that was an attempt, and that's Apollo 13. Great movie, watch it. It'll give you some insights with what happens in space. PRA kind of was brought up on a couple of the previous presenters, but it's a comprehensive, structured, and disciplined approach to identifying and analyzing risk in engineered systems and or processes. Basically answering 3 questions. What can go wrong? What's the likelihood? And what's the consequence? Now, something to keep in mind when people say, well, the PRA team did this or that. The PRA team is actually a PRA analyst, someone that understands the math and the modeling and that kind of stuff, as well as a domain expert, somebody like a subsystem engineer, like an astronaut, like human health and performance folks, the flight surgeons and so forth, because we bring in all the other things other than just hardware reliability. We also bring in things such as external events, micrometeoroids, orbital debris, which we're starting to accumulate around the moon now. We've got tons of it around Earth. So first we got to get through that cloud before we make it to the moon. Other pieces are external events such as the dust, on the moon. I think Clay brought that up earlier too, saying, dust is an issue. You've got to design your lunar surface equipment, suits, all that stuff for handling dust, because that's an environment. That was something we saw on Apollo. And it's still there. And then I think John brought it up, looking at power lines. If we're going to build something on the North Pole and transfer the power down to the South Pole, you're going to have power lines. And how is that going to be? With poles like we do here on Earth, or are you just going to lay the line on the ground? Whatever. How is that affected by the environment we're putting it in? Those are some new questions for us, from my understanding. And as well as looking at the medical risk, if we have people involved, stuff can happen. You have stuff that happens because we're human, or because of the environment we put them into, and they get injured. Slips, trips, falls, if you want to call it, off of boulders or craters or whatever there on the South Pole. Common cause, I think Clay hit on that. That's basically a single point or event that can occur to take out your redundancy. So we need to design for stuff like that. And we do that. We've done that in power industries. We do that in the oil and gas industries I've worked with, as well as here in space. And so it's nothing different. However, power plants, you kind of say, well, we need to protect our hardware. We need to isolate spatial interactions. We put rooms, put this pump in that room, another pump in another room. And if you have a third train, you got a different room. So fires, floods, things like that can take out your redundancy. We can anticipate and help mitigate. Well, concrete and rebar and things like that are kind of heavy to be transferring to the moon. So we've got to think of out of the box here. Let me keep moving on. Let me go on into, so what I'm trying to show is how we're using the Moon to Mars program, the hardware reliability assessments, as well as the comprehensive PRAs, how they work together. That's what I'm trying to get to show everybody. It's not one or the other. You have to use both, because they both have their strengths and weaknesses. They have their purposes. I think as Blanca and Clay and so forth had said, the reliability assessments are really at the hardware and system level. But when you start looking at a mission level, those assessments start falling apart. And that's where the PRA comes into the equation, trying to figure out how all the various subsystems and vehicles and these external events and the human aspects, software risk, all this starts getting added in. Operations, what the crew can and what the crew can't do. How can we handle aborts and other things out there that are possibilities, as well as risk mitigators. And that's what we're trying to do with the PRA. The reliability is helping us design the hardware and subsystems and so forth. The PRA is trying to assess the risk associated with that to help us figure out, where do we spend our money and time? Do we need to work harder on system A or B or C because of the risk that's being shown via the reliability assessments of the hardware, as well as how it's operated with either software or humans in the loop. And that gets to be a big deal, especially for space systems. I think John pointed out, there's a difference between how we do the maintenance on Earth as we do on the moon or even in orbit. It costs more. We understand that. Now, you still have to say, what are our requirements? What are our boundary conditions and so forth? The PRA is not trying to set that up. The reliability assessments aren't trying to set. That's an input into those analytical tools and processes. So it's a iteration approach, an iterative approach, because we are sitting here in the concept phase, right? And wanting to get into that design phase and then get into the operation phase. I've heard a lot of people, not just in this conversation, but, for the last 25 years at NASA, well, you can only use a PRA when you don't know much about what's going to happen. And then I say, well, you can only use a PRA when you know everything. It's like, well, maybe it's a little both. And I say PRAs are used in that concept phase to kind of help capture how things are going to happen and so forth, like we did 10, 12 years ago with Orion and SLS. That was used in the concept of how those programs were developed, as well as how they were designed and now operated. And so one thing to kind of point out, PRA is not trying to answer, it's not a statistical analysis. It's trying to figure out what's the likelihood of something happening that we hope never happens. And that means you don't have a lot of data. And that's why we incorporate uncertainty analysis within the PRA, because I get managers saying, well, how can we reduce the uncertainty? Well, you could do a lot of testing. Oh, well, we can't afford that. I understand, but that's how it all kind of has to be put together to help the decision makers make those risk-informed decisions. And that's one of the prime directives, if you will, PRA at NASA. Let me think. Oh, okay. So NASA, we have these requirements. There's a hierarchy of the administrator, the agency administrator establishes an agency loss of crewed threshold, and that is basically saying that's the most risk that he's or she is willing to accept until the program that breaks it comes forward and let's talk about this. Is it something we can still move forward on or not? That's a discussion at that point. Before you get into a situation like that, the Moon to Mars program is going to be establishing its lock requirements to help, and this is from the crew gets on board Orion at the launch pad all the way to the crew is recovered post-landing in the ocean. And so that's the scope, if you will, of what a mission means, at least to me. And so we're trying to make sure, one, we can handle those kinds of questions and risk at the enterprise level, the Moon to Mars program or enterprise level, before having to go to the agency administrator. Then you get each of the vehicle programs that are supporting the Moon to Mars program. And so, you can see that there's a hierarchy. Everybody's trying to make sure they can do their job, build their vehicle, and not have to deal with the upper management, okay? So that's where the programs have established hardware reliability requirements to provide or impose upon the various providers so that they have something they can work to say, okay, this is what we're trying to build and how we're going to build it and meet the requirements the programs have set for us. And then the providers themselves can then establish their own internal requirements because they may divide up the single hardware reliability requirement from a program. They may divide that up into its various subsystems, aspects, and so forth, and they manage that within their own realm. So there's that hierarchy that I just wanted to kind of point out of how things like PRA looking at the overall mission versus the reliability requirements, looking at the systems and components and so forth, because the PRA doesn't do that and hardware reliability doesn't do some of these other things. So they work together. Let's see, what else? If we don't allocate lock and LOM to providers, one, because there's, we have 6 human space programs going on supporting Moon to Mars right now. There's a lot of variability in what everybody's expertise is within providers, programs, and so forth. My job is to help keep that consistent across all of them so we have apples to apples as best we can. There's nothing perfect out here, so we just do the best we can. And I think you can understand, when you're talking about human reliability, there is some subjectivity involved with that, but there's also 50 plus years of human reliability data out there, all the way back to the 60s, when they tried figuring out intercontinental ballistic missile reliability of the two guys in the silos and so forth. There was a need back then. We have a different need necessarily today for all the applications that we have, whether nuclear power plant reactor operator, or an offshore driller, or a astronaut on the moon or in low Earth orbit, wherever. And so there's just events like this that you want to make sure you're consistent, as well as the folks that are pulling our astronauts out of the capsule or out of the water post landing. All of those have human in the loops, and that's what you're trying to address. You will be doing that when you're building your power grid on the moon. Someone, an astronaut or something, a robot, maybe both, can be involved in doing that. They all have risk contributions that need to be assessed and try to figure out, is there something better we can do or not? Is it good enough? Let's see, what's another? How am I doing on time? 20 minutes over or 30?
Yeah, just 20. Try and wrap up in the next few minutes, and we'll take a couple questions. We're doing okay on time.
Let me kind of jump to what I was wanting to close with, and that would kind of help set the stage for some more questions, I'm sure. But so NASA at the agency level established these thresholds for loss of crew. We don't have that for loss of mission. Loss of mission requirements are established, as well as LOC, at the program levels. That's just the way it is right now. But the agency LOC thresholds are established so we can balance cost, schedule, and risk together, and not try to constrain one versus the other. That's an overall agency and management decision process. The programs have LOC, LOM, and reliability requirements to ensure that we meet those LOC thresholds. It's still, again, LOC is a subset of LOM, and reliability is a subset of LOC, so you can kind of see how some of this goes in. Maintenance, excellent question. That supports loss of mission, because if we have something that's just sitting out there on the lunar surface for years and years and years, something's going to happen. Okay, something's going to fail. We know that. I think, as Blanca was saying, for the next few missions, we got short-term missions. Even the 30-day mission, the window is short. But how long has some of the equipment, hardware, habitats, whatever, been on the surface prior to the 2 or 4 crew members arriving? All those are exposure times for your reliability and maintenance activities. PRA is used to verify LOC and LOM. Reliability requirements are flowed down to providers to enable programs to meet these LOC and LOM requirements. And the providers utilize the reliability assessments to verify their requirements and inform their design. And bottom line, PRA and reliability analysis can be utilized in the development of the lunar grid development to help inform the design and to ensure crew safety as well as mission success. I think that was kind of all the major points I was trying to get in front of you all.
Yeah, thank you so much, Roger. We really appreciate you taking the time. Feel free to put questions in the chat. I wanted to kind of put you on the spot here and ask a question first before we get to what's in the Q&A.
You're the first to ever do that.
Well, you mentioned, going to the moon, we're really going to have to think outside the box, which I think is, hit the nail right on the head. And I wondered if you could speak to any time, in your career doing this kind of work, be it Orion or SLS or anything, an example of something where you had to think outside of the box. Yeah.
Wow. Let me see. Outside the box, shuttle. Shuttle was, well, first, a shuttle PRA versus a power plant or a space station PRA need to be developed differently. And I say that because a space station and a power plant are operating 24 hours a day, 7 days a week, all year long, unless you're refueling for the power plant. But the station's still going on, you know. They still have maintenance things that are going on for both of those in order to continue that operation. Shuttle, everything happens when you hit the launch button. That's when you start looking to see, okay, what kinds of failures could occur at T-6 when the engines fire up, and then what happens at T-0 when the solid rocket boosters fire up, and then when you clear the pad and you're going through ascent and you're shutting off SRBs and you're going through max Q, all the things that go on just to get up the hill. And so then you get into orbit. Now you're acting as a spacecraft instead of a rocket. You know, that trying to understand how to break up a mission from ascent to in space to entry, descent, and landing, as we did for shuttle, was out of the box. There was pieces of work that had been done for a decade or more previously on shuttle, but they focused on ascent because that's where everybody thought 90% of the risk was at. But in reality, you have about as much risk going up the hill as you do in operating in space as you do coming back down. And so it kind of works out to about a third. That's the kind of questions, you know, you kind of have to get out of that box of thinking, I know what the answer is before you start. That's where it bites you. And so just trying to, you know, we have 2 eyes, 2 ears, and 1 mouth, and trying to keep it to more receiving instead of giving, if you will. I'm sorry, I'm quoting some things I use with scouts, but anyway, we have to keep our radar, our sensors up and listening to what the hardware is saying. That was a term that came out after the Columbia accident. What's the hardware telling us? You know, what are we learning from our systems, our data, our testing, and especially as we're going into working on the lunar surface, a lot more than we did 50 years ago. And so that's all new learning experience coming in.
John, did you have a question? You have your hand raised. I wanted to give you a chance before we move on.
It's not so much a question, it's just I wanted to actually just add on to something Roger just said. An example of being careful about being bitten and listening that's applicable to what I just said earlier today. You know, I made the point that the combination of high voltage for transmission and the cislunar radiation environment introduces a new electronics failure mode that we better pay attention to, and that's where we're going to get bit. Now, if I were to make and the implication being that what we've got with the lower voltage systems that we've had a lot of experience with isn't so much of a problem. Based on what Roger just said, if I were to make a statement like that in a shuttle FRR, and I was shuttle flight readiness review, and I was involved with maybe 100 of those over my career, the chair would ask me a very pointed question. Okay, we're not going to learn something, are we? And the tone would be that we really don't want to learn something on the mission. We may have to look inside the box of the 120 volt systems to see how this radiation environment affects them. No, an answer might be, well, we just sent the Orion vehicle around the moon and it didn't have any radiation induced failures. The answer would be, we just got lucky. So again, I think Roger's point's very well taken.
So there's some great insights, and unfortunately, oh, go ahead.
I was going to say, when we do risk analysis, we put, if you will, a chance, 1 in 100, 1 in 1,000, you know, kind of ballparks like that for where some of these risks are falling out. That means 1 out of 100 missions, we have this problem, we have this failure, we lose the mission, whatever. That means there's a good chance 99 times out of 100 we're successful. Excuse me. So as we get into missions where that risk is getting higher and higher, you know, estimates, you know, 1 in 50, 1 in 10, whatever, you still are more likely to be successful than failure, given the work and thought process that goes into the designs and missions we run and so forth. But that doesn't mean they're going to be perfect. Nothing is perfect. Nothing has zero risk. So we're just trying to identify what can go wrong and try to minimize the probability of that occurring. I think that's the goal of this whole, well as build what the grid's going to look like on the moon, but trying to do it as best we can.